I would like to thank BPCL and CST for giving me opportunity for speaking here in front of all the learned people. So today I am going to share BPCL's journey, how we have transformed our current usage of Aviva Spiral from basic crude asset management tool to the advanced optimization tool. For every LP planner or user, the two most important and challenging tasks are how he can simulate the whole refinery, complex refinery processes in simple mathematical equations, which can provide him more accurate and fast results. Second task is how he can minimize the plan versus actual gap. Because this plan versus actual gap or deviation means we are losing margin. So as Manoj talked about how plan versus actual as we are bleeding money in project stage. So here I'll be discussing about how plan versus actual gap we are bleeding money in case of our normal refinery operations. So these are the 5 challenges, operation challenges a LP planner faces, how he can model all these 5 challenges in his day-to-day planning. One is slow processing. Every refinery processes slow, but during his LP run, he is not able to include those conditions in his plan. Second is intermediate product. So all the refiners want to sweat their secondary units. So for that, sometimes they purchase intermediates like high sulfur diesel, high sulfur VGO and other intermediates so that their downstream units are sweating. But it is very difficult to calculate the break-even cost of that. So that also we'll see how we have modeled that. Second is special operating conditions. So that special operating condition is from one of our refineries where we take periodic shutdown of our vacuum column. At that time, our crude unit will be running at reduced throughput, and vacuum atmospheric column will be bottom will be routed to my crude tanks. That will be reprocessed later. Second is crude evaluation complexity. So here we'll see how with a single click we'll see directionally which are the crudes will show more value to our refinery. Third is cut point constraints. Cut point constraints, currently we use static cut points in our basic asset management. So sometime in actual operation we'll change the cut point of cut points of crude unit, but this how it impacts our profitability, that also we'll see. So with this aim, we started our journey with the aim of reducing the gap between plan versus actual. So whatever we plan, we'll get actual out of it. Second is how we can model the complex scenarios like slow processing, how we can get the more accurate value of break-even values of our intermediates. When going to market, we should purchase intermediates at more accurate price. Second is how fast we can take decisions, and while doing my crude evaluation, I should not miss any crude. Third is this. Fourth, how all these decisions I can take with the data available with me. So we'll start with slope tank modeling. So all the refineries reprocess slope. So based on the 3 conditions, they will limit the slope processing. One is physical constraint in the crude unit. Third is metals and sludge. So metal and sludge, we cannot model it. But the physical constraint we'll model it, we'll utilize assay synthesis capability of spiral, and we'll take 2 to 3 properties we'll test in our lab and generate a pseudo assay of our slope tanks, and that will integrate with our PIMS output, and then we'll get whatever we plan, we'll get in actual also. So this is how we'll simulate my actual planning with my LP tool also. Third is ISDs. So few refineries have capacity available in downstream, so they want to purchase high sulfur diesel, high sulfur VGO, all the ISDs they want to purchase. But challenge is how to calculate the break-even cost of that. Another thing, there is infrastructure limitation, how they can take those intermediates inside the refinery. So only option left is they can take this along with the crude, and that will be processed in the crude unit and then subsequent to the secondary units. So how to calculate the break-even cost of that? So here we miss 3 major things. One thing is when we are taking all these things in crude tanks and processing atmospheric column, So there will be physical constraint in the crude column that will not be available with us when we are doing with basic crude management tool. Second is, there will be always having inefficiencies in my tray columns. So that will not be taken care in my normal process. And third one is how both we can take and calculate the more accurate utility consumption of crude unit also. So all these things, so what we'll do, we'll use the product synthesis tool of Aviva Spiral. In that, we'll generate the pseudo crude assay of that particular ISD and take that in crude unit, and there we'll be able to calculate more accurate break-even values. This is one issue we face in our refinery. So in that, during plant shutdown, we'll take a shutdown of our vacuum column and we'll run our crude unit at reduced throughput and route our RCO to crude tanks. That will be processed subsequently in the coming month, and vacuum column is available. But how to model that in our normal operations and how we can get this output without doing any manual intervention outside the LP tool. So what we did here, we have taken a single crude and then distributed that crude in two parts using product synthesis and stream synthesis feature of Aviva. In that, a single crude is broken in two parts. One is from IBP to the atmospheric column bottom, and then second is from vacuum diesel to the VR. And there's two crudes are processed in the refinery. With that, we are able to get more accurate results, and our plan versus actual gap is also minimized. Here are this freeze point. So this is one major issue faced in our refinery. So different crudes, kerosene has different freeze point. So what issue we are facing, that whenever we are processing certain crudes, we are forced to reduce the kero cut point. So whatever kero was dropped, it was getting dropped in diesel. So our diesel treaters were already saturated and we were forced to reduce the crude charge. So in this scenario, instead of using the static cut points, we use the property target feature of Spiral and made dynamic cut points. In that, my cut point will depend on my freeze point. With this, it helped me in getting better crude evaluation, and I'm more close to my actuals. Fifth one is straight run product value. So every refinery have different process to evaluate crude. In BPCL, every week we evaluate 300 to 350 crudes. So after 350 crudes also, there are chances that we'll miss some crudes. So how to ensure that all the crudes are evaluated? We are not missing any single crude. So straight run product value will not give the exact output, which crude we should buy, but this will give direction that these crude should be evaluated. So what we'll do, we'll take the products of the crude unit and see based on refinery configuration. Suppose my high sulfur diesel is there, if I'm processing, which product it will make. If high sulfur VGO is there, how much product it will make. Based on that, we'll arrive at the product values, and that product values along with the constraints like how much naphtha a refinery can process, how much sulfur and nitrogen refinery can process, all these constraints and prices will put in our Spiral. And with a single click, we'll see the crude values of 5,000 crudes. In that, we can filter out, okay, these are the crudes I should target. In my current evaluation, these crudes are not missing. So we have three use cases in that. One is vacuum residue reprocessing. So one of the scenario was we were facing furnace well containment because of reasons of bitumen evacuation issue and delay in tanker arrivals. In that, we are forced to route our vacuum residue to our crude tanks, which were reprocessed later. So same thing with the help of product synthesis. We have taken samples and we divided which VR we have routed to the crude tanks. We generated a assay out of it. And with that, we are able to predict how much FO I will be generating when I process crude from those tanks. So this helped me in avoiding distress export of FO. Third is, already discussed that we'll take shutdown of vacuum column and crude units will be running at reduced throughput, and RCO will be routed to crude tanks, will be reprocessed later. So this process also we have used, and we are able to match the gap between plan versus actual. And we are again able to predict our FO generation. This is how high sulfur diesel import analysis we have done. So in our Mumbai refinery, we have a spare capacity available in high sulfur diesel units. So we evaluated how we can calculate the break-even cost of high sulfur diesel if you want to buy from outside. So, but there is no infrastructure available. Only option is I can take along with the crude, then store in the crude tanks, then process in atmospheric column, then subsequent to secondary units. If I calculate the break-even cost with normal method, I will not get the operating cost of crude unit and other inefficiencies of crude column, because I will take diesel because of overlapping of the streams in my crude column inefficiencies in the tray. I will not get the whole diesel. Something will go in naphtha, something will go in VGO also. So all these things we modeled with the help of product synthesis, and we were able to calculate the more accurate break-even cost. With this, we leverage the existing tool capability without any cash outflow. We use the existing tool capability and we match the plan versus actual gap, and so this is our way forward. So we want to use all these capabilities in our future planning and operations, and we will see how we can use this for evaluating our future projects and how we can implement this for digital twin also. Thank you.